Hello everyone! One of the limitations of the use of value design engineering at the project design engineering documentation stage in the framework of the implementation of projects in the engineering industry is the lack of awareness of project managers and chief designers of the project about the possibility of using the value design engineering tools regulated by the current regulatory documentation, in particular the United System of Design Documentation. Other limitations include the lack of the necessary culture and qualification of design engineers in the field of using value design engineering tools in the design process, the lack of cost engineering departments within the design bureau, and the ability to support the design engineering process, the lack of specialized information systems for managing product costs, the lack of necessary culture and qualifications for using value design engineering analytical reports from the project management, and etc. The issue discussed in the video Value Design Regulatory Support relates to Block 2, School of Value Design Engineering of Training Course, Cost Engineering. As part of the review of the regulatory support of the value design engineering, I will not refer to the educational and reference literature. In particular, numerous textbooks and reference books on the value analysis, which usually contain sections on the value design engineering, as well as scientific publications, and give students the opportunity to familiarize themselves with them independently. Such a restriction is due to the purely practical orientation of the value design engineering cases under consideration. Therefore, there is only regulatory documentation that we will review as the current domestic and international standards governing the methods of displaying the structure and functional of the product. The following two standards are closest to the subject of the value analysis on the first view, and its sections such as cost engineering or cost design engineering in value design engineering. GOST 58535 cost engineering terms and definitions, and GOST 57306 engineering terminology and basic concepts in the field of engineering. However, in my opinion, in the context of considering the value design engineering, it doesn't make much sense to refer to the content of GOST R 57306 due to its obvious bias towards the development industry, as evidenced, for example, by the terms listed in the section Terms and Definition. In terms of practical value design engineering, it's also not necessary to overestimate the importance of GOST 58535, the creators of which are thought they claim to be general in scope and universality. In the first approximation, its scope is indicated by the following areas: construction engineering, investment and construction engineering, technological, biotechnological engineering, system engineering, non-engineering, venture engineering, etc. Thus, the positioning of engineering and mechanical engineering, if mentioned in this standard, is either within the field of system engineering or within the field of venture engineering, i.e. in a very general way. Thus, the use of both of the above standards, which would seem to be closest named to the topic we are considering, in the activities of a design engineer and mechanical engineer, in my opinion, doesn't make much practical sense. A detailed review of compliance within the concept set out in GOST 15016 technical assignment requirements to contents and form of presentation, with the formulation of the basic definitions of functional cost analysis, which includes functional and structural models, has already been performed in issue number 10, Analogy of the Value Analysis Methodology and Technical Specification Information Approaches. Anyway, since the technical assignment refers to design engineering documentation, describes in the first approximation the functional composition of the product, and is the basic design document in the development process within the framework of the requirements of United System of Design Documentation GOST 15016, is certainly one of the normative documents regulating the possibility of using value analysis and value design engineering in the process of design engineering's work. It should be noted that in paragraphs 4.4 and 5.2 of GOST 15301, procedure of product development and launching in the manufacturer, it's mentioned a document replacing technical assignment mutually recognized by the customer and the developer, which can be just an alternative form of technical assignment in the form of an extended or text functional basis, the format of which was proposed in issue number 10 of our training course. GOST 2.103 Unified System of Design Documentation, Stages of Designing, is relevant to the value design engineering to the extent that regulates the compliance of the stages of development of the design engineering documentation for the product and their compliance with the stages or milestones of the project, i.e. it's a question of the degree of synchronization of structural and functional models with the design engineering documentation at the stages of the project. It's not coincidence that the list of keywords for this issue contains two editions of a similar standard, namely GOST 2.053 2013 and 2.053 2023, named Product Electronic Structure General Provisions. This conditional duplication is due to the differences in terminology as well as the degree of abstraction of the consideration of the concept of forming the electronic structure of a product. Thus, consideration of the 2013 standard, albeit cancelled at the moment, gives, in my opinion, a more holistic picture of the possibilities of using value design engineering tools within the framework of forming the electronic structure of a product. With regard to the content of the scope of application section, it can be noted that in the 2013 version of the standard, it's proposed to develop standards based on it that take into account the specifics of the electronic structure of the product at various stages of the life cycle. In particular, the formation of standards governing the formation of structural and functional models is relevant for the stages justification of the development, development of technical specification, conducting research and development of the product life cycle, see GOST 53791. In the standard version 2023, there are no references to the changes in the structure requirements depending on the stage of the life cycle. The section's normative references and bibliography haven't undergone significant changes, however, they have been partly supplemented by GOST and International Standard Organization series standards. In GOST from 2.053, from 2013 year, a fairly abstract definition of the product structure is given, namely the structure of a product, the set of component parts of a product and the relationships between them that determine the hierarchy of component parts. Thus, in the definition, there is no division into the functional and physical structure of the product corresponding to the terminology used in functional analysis. In GOST from 2023, the situation changes significantly, since two definitions of the structure, functional structure and physical structure, instant structure, physical or instant structure, introduced. Therefore, we can draw on almost direct analogy with the terminology used in the value analysis. In this case, it's implied that functional model is an analog of the functional structure and structural model is an analog of the physical structure. In this case, it should be taken into account that both terms are translations from English. In particular, the translation of the terms functional structure and instance structure. The functional structure is GHOST means the structure of a product formed from elements describing the functions, the product and its components and connections between them to display the method or methods of its intended use. Perhaps such an analogy will seem far-fetched to someone, but in my opinion, this definition is so good that I could see it as an alternative to the definition for the functional model given in issue number 7 of our training course, Objective Analysis, Decomposition, Formulation of Functions. I like the wording of the definition of physical structure or structure of an instance from GHOST 2023 less, and it sounds like this. A physical structure is a structure of a product, the elements of which are actually established specific instances of component parts. In the case of using the terminology adopted for the cost engineering course, actually installed specific instances can be replaced by the physical carriers of functions. GHOST from 2014 provides a definition of the information model, which is also quite abstract. GHOST from 2023 doesn't have it, taking into account the fact that the both standard model and functional model are models belonging to the information class, that the presence of this definition can be considered as an indirect confirmation that when displaying the structure of the product, in this case, value analysis tools can be used. As a result, according to the section Terms, Definitions and Abbreviation, it can be concluded that in GHOST from 2013, an attempt was made to form a list of as general definitions as possible, allowing to expand the possible options for their interpretation in GHOST from 2023. The meaning of the terms is narrowed and approximated in meaning to the terminology used in the value analysis. In the section Basic Provisions, clause paragraph 5.5 of GHOST 2.053, paragraph 5.4.5 deserves attention, indicating the possibility of forming an electronic structure of the product, regulated by GHOST 2.102 of United System Design Documentation, named Types and Sets of Design Documentation, whose relationship with the value design engineering will be discussed in this issue below. The section Basic Provisions, paragraph 4.6 of GHOST from 2023 has been significantly revised compared to GHOST 2.053 from 2013. However, it's also stated in the modified form that in the automatic product data management system, graphical and textual elements of the product electronic structure can be associated documents as well as information object containing information about the properties and characteristics of the corresponding elements or from product components. Information about properties and characteristics can be presented in various forms, quantitative, descriptive, in the form of calculation models, and etc. I think listeners like me can easily draw the parallels between the description of structural and functional model, as well as analytical reports and characteristics of documents listed in the main provision section, thus in United System of Design Documentation, and in particular in paragraph 4.6 of GHOST 2.053 from 2023. Obviously, it provides for the possibility of forming such a value design engineering tool as information database on the cost engineering system. A separate issue will be devoted to this issue related to the design product electronic structure within the framework of an automated product data management system. The 2013 standard contains two sections: general requirements for the implementation of product electronic structure and general requirements for the structure of product electronic structure. In the section of general requirements for the completion of the product electronic structure, In the context of the requirements for the uniformity for the presentation of product and electronic structure, as well as the languages and forms of description of information models used reference is made to the ISO 10303 series standards, which will be discussed below. In the section devoted to the general requirements for the content of product electronic structure, paragraph 6.2 states the next. For the same product, depending on the stages of the product life cycle, varieties of product electronic structure can be developed and applied, performed on the basis of determining specific aspects of the product description or context. The nomenclature of the information objects used, the technical content, and the corresponding data model are established by the developer unless otherwise defined in the technical assignment. Thus, in accordance with paragraph 6.1, it's allowed to form alternative product electronic structure not only at various stages of life cycle, but also at various milestones of the project, both outside of product design management system of the project, for example, local files on the server of the production costs analysis department, and within the PDM system in which special items have been created to work with information objects of the stage of design engineering documentation. The following main types of product electronic structure are listed in clause or in paragraph 6.2. Functional, constructive, and production, and technological, physical, operational, and combined. Further, in paragraph 6.2, explanations are given about the purpose of functional, constructive product electronic structure, which I will not give verbatim in order to save the interest. Listeners can familiarize themselves with themselves. I will only note that with regard to the functional product electronic structure, its applicability has been established, namely the milestones of the technical proposal draft and technical design, i.e. in the context of the design engineering documentation. There is no such restriction for a constructive product electronic structure, since it can also be clarified at a milestone corresponding to the stage of development of the work and design engineering documentation, since it's main design document. I believe that listeners familiar with the previous editions devoted to the theory of value analysis, as well as I will draw an obvious parallel between the first two types of product electronic structure, namely functional and constructive product electronic structure, and functional and structural models in value analysis and value design engineering. The rest of the varieties of product electronic structure listed in paragraph 6.2 are not related to the value analysis and value design engineering, and are used within the framework of technological instance, operational and combined integrated analytics at various stages of life cycle and displays of product electronic structure in the PDM system. The 2023 update of the standard doesn't not contain a detailed description of the concept of forming the product electronic structure classification, which was given in the 2013 version, but the classification itself remains unchanged. An analog of paragraph 6.21 of the 2013 standards confirming the possibility of using alternative product electronic structure characteristics of the value design engineering, we are talking about structure and functional model, is paragraph 5.3.6, which reads as follows. It's allowed to introduce other types of document containing other types of product electronic structure, as well as to use combined product electronic structure combining separate varieties of product electronic structure for presentation and displaying comprehensive product information. Additionally, the 2023 version introduces the designations of product electronic structure varieties FES, functional electronic structure for functional product electronic structure, and FCES, functional carrier electronic structure for constructive product electronic structure. The applicability of the design engineering documentation development stages is similar. Functional electronic structure is a stage of the design documentation and function carrier return structure is a stage of design and working design documentation. In addition, two varieties of function carriers return structure have been introduced depending on the content requirements. The first, the basic function carrier return structure includes information about the structural parts, components directly included in the product and doesn't include the FCS of these parts. And the complete functional carrier return structure includes information about the structural parts or components directly included in the product and their structures, functional carriers, and structure of the structural part, with the exception of the structure of purchased products. Generally speaking, this classification, basic and complete FCS, once again confirms the similarity of approaches to the formation of the function carrier and return structure and the classification used in value analysis and value design engineering, because, in fact, basic and complete function carrier return structure is nothing more than structural model of varying degrees of abstraction, except that the terms of full structural model in the value analysis and value design engineering designates a structural model displaying all the elements included to the design, including fastness, standard products, etc. In the case of full function carrier return structure, there are no decomposition requirements for purchased products. In paragraph 4.1, Note 2 of GOST 2.051, United System of Design Documentation, Electronic Design Documentation, General Provisions indicated. The design engineering documentation may also include various computer models, mathematical, computational, etc. used to justify decisions. Thus, the basic tools of the value design engineering fall under this category of design documentation, in particular structural and functional model, an alternative form of technical assignment, and analytical reports, which are the text, tabular, and graphical, diagrams or histograms, computer model used to make design, technological, and economic management decisions. In process of implementing the business process of functional and cost design, a number of issues arise related to the possibility of accounting for analytical documentation, including as intangible assets, as well as the inclusion of analytical documentation and the design documentation said the development of which is stipulated to the contract for the implementation of the research and development. The question naturally arises to which group of documentation can structural and functional model be attributed, and analytical reports in accordance with the United System of Design Documentation. The simplest solution in this case is to clarify its other documents in accordance with the classification given in GOST 2.102 of United System of Design Documentation. In accordance with the symbols given in GOST 2.102, other documents refer to the optional documents, i.e. documents the need for the development of which is established either in terms of reference for development or is established by the developer organization based on the characteristics of the development object. With regard to the ISO 10303 standard named Industrial Automation System and Integration, Product Data Representation and Exchange, often mentioned in the GOST 2.053 standard, and at first glance having judging the name a direct relationship to the topic we are considering, I can conclude that following the designer is unlikely to refer to the standard in the process of functional and cost design, since the standard is intended for the specialist on the computer representation of product data and data exchange. However, separate comments on this series of standards should be voiced. This standard, firstly, is a translation from English with all the results differences into formulation of basic concepts, and secondly, it's intended not for technical specialists, but for programmers, specialists in working with information databases, and business process specialists, i.e. specialists using their own professional terminology. These two factors cause some differences in the basic definitions, which is noticeable even with a cursory examination of the GOST ISO 10303, Part 1 standard, which describes the general scope and describes architecture as well in the structure of ISO 10303. An example of such differences in the section terms and definitions, which presents individual terms similar in sound or abbreviation to terms used in the cost engineering and United System Design documentation, but having either a completely different or significantly different meaning. It's a mistake. Here should be ISO 10303 here. For example, in GHOST ISO 10303, the applied functional model have the next form. Is a model describing an applied subject area through processes and information flows. A similar abbreviation having completely different meaning in cost engineering is the complete functional model, CFM, in value analysis engineering in our course. The second example, assembly unit. In ISO 10303, assembly is a product that from point of view of given subject area can be decomposed in a set of component parts of common assembly units. And in the United System of Design documentation, this term had the following wording: an assembly unit, according to GHOST 2.101, is a product, the components of which are connected to each other at the manufacture by assembly operation: screwing, articulation, riveting, welding, soldering, pressing, rolling, gluing, stitching, laying, and etc. The next, an integral part or component is a product that, from the point of view of this applied subject data, is not subject to decomposition. In cost engineering, as we know from the previous releases, an object of analysis, which in turn is subject to further decomposition, since it's impossible to carry out a functional cost analysis with respect to an object that cannot be decomposed. And the last example, the product. Product is an object of a substance produced or a result of natural and artificial process. In the United System of Design documentation, product, in accordance to GHOST 2.005, a product is an object or a set of production items to be manufactured in an organization according to the design engineering documentation. In terms of foreign standards, a series DIN and VDE standards should be noted firstly at the closest in terminology to the domestic school of value analysis, and secondly as a fairly complete system of standards that provides a comprehensive description of the general business processes of cost engineering, both at the level of design and local analysis at the level of project management, i.e. teamwork. The first and the most general standard that I would like to mention is the DIN 1325, Value Management Dictionary Terms. The standard provides the most general definition of value-based management. In particular, it mentions such concepts as function structure, function analysis, cost of function, design for a given cost, optimization and value creation, product effects, and etc. In addition, the standard introduces a distinction between the functional analysis into functional needs analysis related to marketing, and technical and functional analysis, or functional cost design, or functional design engineering in our terminology. To use domestic terminology, we named it value design engineering. The next point to consider the standard DIN the 12973. Value management. The introduction of the standard indicates that the purpose of its creation is to describe and define value-based management and provide guidance on the implementation of fundamental concepts, approaches, basic principles, value factors, procedures, and tools for effective management. In fact, the standard has no practical value for the design engineer, since, like the above mentioned DIN 1325 standard, it's quite general. The audience of the standard is top-level managers, methodologists engaged in writing cost management regulations, chief designers, and project managers. The most interesting thing in the standard, in the concept of practical cost engineering, is, in my opinion, a table with a work plan for the functional cost analysis, a table of responsibility allocation during functional cost analysis, and general description of generally accepted methods of functional cost analysis, as well as examples of tabular cost matrices for functions. The following standard is called VDI 2803. Part 1, Function Analysis, Fundamentals and Methods, outlines the basics of the formulation of functions and their classification. Different from those that we discussed in issue number 7 of the course Cost Engineering, in my opinion, the standards is also quite general and difficult to apply in practice. However, for general development, I would recommend that students familiarize themselves with the standard. A significant place in the standard is given to the FAST functional analysis system technique method, which, for example, I do not use in practice. Firstly, because working with flowcharts and correcting them is quite time-consuming, even if special software available. Secondly, due to the complexity of understanding by design engineers and cost design engineers. The advantage of the FAST method is the convenience of visual perception of information. The name of the next standard has a reference to the standard that we already discussed above, VDI 28.0. Standard Part 2, Value Analysis Work Plan according to the DIN 12973. Complicated name. As you can see from the name, this standard is a detailed version of the description of the value analysis work plan given in the general form in the DIN 12943 standard we have already considered. The practical value of the standard is the presence on it of a large number of working tabular forms corresponding to the stages of the value analysis which can be used in practice. The next, VDI 2808. Standard named Evaluation and Value Analysis Methods and Tools regulates the methods of assessing significance, which in a more expanded form compared with the standard form that we will be discussed in issue number 11 of our course. However, it's the same as in the case of VDI 2803 Part 1, Function Analysis, Fundamentals and Methods. I would recommend the students familiarize themselves with the standard to broaden their horizons. The features of the standard include the consideration of this assessment of significance in the context of the work plan in accordance with the DIN 12973 standard, the availability of the list of methods for assessing significance, indicating the required level of detail of data, intensity and, of effort and commands as well. The section related to the visualization of the results obtained. The next standard that we will consider will be the VDI MT 2807. Standards, teamwork, application and value analysis and value management projects. The standard describes the advantages and describes the process of teamwork, the composition of the team, the necessary qualification of the functions of team members, management styles, and teamwork. In a series of videos, implementation of value analysis, all these problems of implementation of value analysis in the standard will be included in the standard, but we will consider them a little more deeper. In the issue of assessing the complexity and financial cost of organizing the value analysis, both within a permanent unit and within a local mini project, as well as some other issues. Among other things, it should be mentioned the existence of such standard of VDI 2817, Part 1, Performance Pricing, Fundamentals and Application, which is indirectly related to the group of standards discussed above in the context of the possibility of applying the value analysis in the process of forming target values of direct costs for a product based on their significance and subsequent formation of the selling price subject to a given margin. Speaking about non-diversified foreign standards, I noted only those that I had opportunity to familiarize myself with in full, namely to the VA and VDE standards shown on the slides. As I have already noted in previous issues, in addition to publicly available standards, there are intercompany standards, access to which is limited. The use of the video format, unlike the format of scientific articles or dissertations, doesn't necessarily imply the presence of scientific novelty. Nevertheless, I wanted to draw the attention to the audience to its presence. In particular, the regulatory documentation discussed in this issue already mentioned above assumes the use of value analysis and value design engineering tools only as a stage of design documentation. See GOST 2.1.103. However, in our course, in particular in practical cases, the possibility of wider application of these tools will be considered. Firstly, when forming the alternative form of technical assignment. Secondly, when forming the complete structural and functional model, displaying information about the object of analysis to the extent of abstraction, allow information transfer according to this cycle, design documentation, structural functional model, design documentation. Without loss of information, thus in the course cost engineering, we cover the stages of both design and working design documentation. It should be noted that what if form from the loop design documentation, structural functional model design documentation, replace the component design documentation with a reverse engineering object at the first stage of the cycle, then we will get nothing more than a visualization of the concept of performing reverse engineering with the value analysis tools, i.e. this cycle. If we consider the typical definition of reverse engineering in more detail, it can be noted that the condition which sounds like the development of object similar to the original in functional composition, but without direct copying. This. In practice, often causes difficulties if considered outside the context of functional cost analysis, whereas in the context of the value analysis and the value design engineering, all at once, it falls into place since a similar functional composition can be achieved to the similar functional model is used to the value design engineering process, whereas the structural model modified for various reasons, customers' wishes, technological reasons, material replacement, change of the power circuit, and therefore the electronic structure of the product and the corresponding design documentation will differ from the original reverse engineering object, i.e. the condition will be fulfilled. In the table presented on the slide, two types of reverse engineering are considered: basic, without the use of value analysis and value design engineering, and advanced. The case of basic reverse engineering without the use of value analysis and value design engineering is typical for most companies offering services in the reverse engineering market. The technical feature of this approach includes the possibility of obtaining a product visually and functionally similar to the original one, with changes due to the wishes of the customer, technological nuances, material replacement, a change in the power schema operational, the need for strength calculation, etc. Thus, the only obvious disadvantage of this approach is visual identity, which can cause legal claims from the developer of the original reverse engineering object. Technical assignment in most cases of reverse engineering are not formed for reasons of the economy of resources, since the required characteristics are already known and correspond to the characteristics of original reverse engineering object. The economic feature of this approach, first basic approach, The economic features of this approach include the absence of the stage of development of an economic model of its visualization, which make it possible to assess the compliance of the new design with a target indicator of direct costs for aggregation systems. In addition, in most cases, again for reasons of economy, there is no such stage of development as the information of an action plan to reduce the direct cost of a new product. Such a technique of the method of factor research in principle can be applied. However, as noted in video number 9 of our course, the effectiveness of its isolated application or application without the formation of structural functional model is quite low. Thus, in the case of the basic reverse engineering, only the final actual calculation of direct product cost is available to the customer, significant adjustment of which by changing to the design is no longer possible. In the case of extended reverse engineering, with the use of value analysis is used less often due to the occurrence of additional costs for attracting a cost engineer to the project team. However, the minimum expected reduction in direct costs, if applied, is in the range from 5 to 10%, which in most cases covers the costs associated with attracting a cost engineer. In addition, the availability of deployed cost analytics can become a competitive advantage when choosing a contractor due to the possibility of providing additional features such as correction of the functional model of the original reverse engineering object by excluding or adding individual consumer or other types of functions to it. In the case of functional model, partly plays the role of technical assignment that allows you to divide functions into basic and additional ones so that the customer has more design options during the development process. Development of an alternative form of technical assignment, the advantages of which, such as visualization of the costs of function and function carriers, the ability to compare the ratio of significance, quality of implementation, and costs by constructing diagrams RQS and FOS, were considered by us in issue number 10 of course Cost Engineering. In terms of visual similarity to the original reverse engineering object, advanced reverse engineering also has a number of advantages due to the fact that after adjusting the functional and structural model and subsequent formation of a design engineering documentation set based on them, the new object has less visual similarity to the original object. A number of practical cases of Block 2 will be devoted to the topic of reverse engineering with value analysis tools. Based on the results of the analysis of the regulatory support of the value design engineering, it can be concluded that the value design engineering and its main tools such as structural model, functional model, alternative forms of technical assignments, and various types of analytical reports are firstly tools for forming the electronic structure of the product at the design stages of design documentation, development, see GOST 2.103. Secondly, the first allows you to supplement the list of existing visualization options such as multi-level and graphs lists, like graphs that described in GOST 2.053 due to the visualization methods used in the value design engineering. Thirdly, they allow us to assess the degree of balance of design according to the criteria RQS, or importance of the function, quality, the implementation of the function, and cost for function. The basic tools of value design engineering, in particular tabular, structural model, and functional model, in turn, fully meet the requirements set out to the United System of Design documentation under the code. Other documentations, see GOST 2.102. For such elements, product electronic structure, and as in function carrier, marked as function carrier ES or FCES, and functional electronic structure or FES, and design stages of design documentation development. It should be noted that value design engineering tools have an advantage over multi-level lists and graphs, which are widely used today in the most product lifecycle management systems, consisting in the initial orientation of structural and functional model on the formation of analytical reporting, which allows evaluating parameters such as significance, degree of satisfaction, and direct costs for individual function and their carriers. In addition, a distinctive feature of the value design engineering tools is the ability to translate or convert such classic documentation as technical assignment, 3D models, and drawings. We are talking about the low degree of abstraction or full structural and functional models. To translate into the functional model and the structural model format and back without loss of information. Such data conversion qualitatively distinguishes value design engineering tools from multi-level lists and graphs, which are essentially abstract information, graphical models not used in value analysis, for a number of reasons, including due to the high complexity of their construction and adjustment in comparison with tabular models. An example of converting technical assignment into an alternative form in the form of structural functional model and analytical reporting. We're talking about basic and advanced versions of technical assignment, has already been considered by us in issue number 10, Analogy of the Value Analysis Methodology and Approaches to the Formation of Technical Assignment. Examples of converting 3D models and drawings will be considered in the framework of practical cases on the Value Design Engineering course, along with the ability to convert data in accordance with the cycle design documentations to structural and functional model form to design documentation form. A competitive advantage of classical or basic reverse engineering has a direction related to the use of advanced reverse engineering. Based on value analysis and value design engineering tools in accordance with a modified cycle, we change first stage design documentation to stage reverse engineering object analysis. And we have new cycle, first stage reverse engineering object to structural and functional model and to design documentation. That's all for today. All bye.